Good morning and welcome to Analog Electronic Circuits. This is lecture 7. So, in the last class we were looking at what it meant for a signal to be a large signal, and we said that an incremental gate source voltage where the swing is much smaller than twice VGS minus VT is what is considered a small signal. And then we went on to start looking at what actually happens when the input signal swing is increased. So, Vi is nothing but A sin some omega t. Omega is assumed to be sufficiently large that input capacitor, coupling capacitor can be considered a short circuit. Okay. And we said let us take a look at the absolute waveforms at the gate and the drain. So, at the gate the absolute waveform, the total waveform will be the sum of the quiescent quantity and the incremental quantity. The quiescent value is VDD times R1 by R1 plus R2, and on top of it now you are going to have a sinusoid with amplitude A ride. Okay. And the drain potential is going to be, the quiescent value is going to be VDD minus ID times RL, and ID can be found the moment we know the properties of the transistor, and the total voltage at the drain is basically the sum of the quiescent and the increment again. The incremental voltage at the drain is what now? Minus GM RL times Vi. So, this amplitude, that distance is A. So, this must be, so somewhere there, right. So, this distance must be GM RL times A, right. So, in the positive half of the input cycle we see that the transistor is going towards, it is going towards the triode region, right, and if the input A increases beyond a certain limit, what will happen? First, of course, the drain potential will go below the gate potential, and if you increase the amplitude even further, what happens? The drain potential will become, yeah. So, remember that the condition for triode is what? VDS equals VGS minus VT, which in English basically means that the potential of the drain goes 1 VT below that of the gate. Okay. So, now the question is, so the first question that we would like to ask is, what is the largest input one can put so that the transistor remains in saturation, right. So, A max 1 is the maximum input amplitude when the device, when let us call this M1, just enters triode. Okay, how does that look like? So, in that case what happens? Well, we are only looking at the positive half cycle. So, this is absolute potential of the drain. So, at which point in time will you have the transistor going closest to the triode region? At the peak of the input, that is at that point. So, what comment can I mean, so if the transistor we know is in the edge at the edge of the triode region, what comment can we make? What is that distance? Vt, that is all, right. So, what is the what is the peak value there? What is the absolute voltage there, fellows? Yeah, this is basically VDD times R1 by R1 plus R2 plus A. What is this? What is this character now? That is VDD minus IDRL, or this if we call this A max 1 minus IDRL minus GMRL times A max 1. Correct. So, the condition for just hitting the triode region is VDD times R1 by R1 plus R2 plus A max 1. Yes, what do we minus Vt equals VDD minus IDRL minus GMRL A max 1. Okay. And just do some algebra. So, A max 1 times 1 plus GMRL equals VDD minus IDRL minus VDD times R1 by R1 plus R2 plus Vt. Okay. What is this actually? Yeah. So, that is VDS minus VGS, that is VDG, right, under quiescent circumstances. All right. So, therefore, A max 1, which is the maximum sinusoidal voltage you can apply before the transistor goes into the triode region, is given by VDG quiescent plus Vt by 1 plus GM R. Does it make sense, people? Okay. Now, that is the story in the positive half of the input cycle. Now, we have to worry about what happens in the, by the way, in the positive half of the input cycle, what comment can you make about the waveform of the current? It will be, the quiescent value will be some ID, total current will be the incremental current. What is the model for the transistor? So, incremental current is in which direction? Does it flow downwards or upwards? Downwards. Yeah, you clear now? Okay. Small ID. So, what is the total current? It is a capital ID, which is the quiescent value plus Gm times A times sin omega t. It will be in the same direction as it will be very similar to the blue curve, except that the average value will be a capital ID and the amplitude will be Gm times A max. Does it make sense? All right. Now, let us worry about what happens in the negative half of the input cycle. In the negative half of the input cycle, the drain potential is the gate potential is increasing or reducing? Is reducing. What comment can we make about the drain potential? Drain potential is increasing. So, is the transistor going deeper into saturation or closer to triode? It is going deeper into saturation and in this general direction, because the what do you call the gate source voltage is reducing and the drain voltage is increasing. Okay. And what do you call what comment can we make about so there is the bottom line is that in the negative half of the input cycle there is no danger of the transistor getting into the triode region. On the other hand, what comment can we make about the total current in the transistor? The quiescent value is ID, right. In the positive half of the input cycle, the current was doing this, and this is basically Gm times A, all right. So, in the negative half of the input cycle, this will be ID minus Gm times A. So, what is the minimum current? ID minus Gm times A. So, now the question is, what is the maximum input? So, what is happening? I mean, if A becomes larger and larger and larger, what comment can you make about the minimum current in the transistor? It is reducing, and eventually what can happen? What is the lowest it can go to? The lowest it can go to is 0, correct. So, therefore, what is the maximum amplitude A max 2 maximum amplitude So, if the input amplitude is increased more and more, the minimum current will become ID minus Gm A, and the maximum input A that you can use before the transistor gets cut off is nothing but yes, what is it? ID minus Gm times A max 2 must be equal to 0, would give you the limit for A max 2, and that therefore is A max 2, therefore is nothing but ID over Gm 2. And can you write Gm 2 in terms of ID? That is basically 2 ID over VGS minus VT, which is VGS minus VT over 2. Okay. So, let us take a step back and summarize what we have done. We have a common source amplifier, we have figured out what the small signal properties of the amplifier are. Then what did we say? We said that if you go on increasing the amplitude in the positive half of the input cycle, the transistor is going towards the triode region. So, if you go on increasing the amplitude beyond a certain point, the transistor will just enter the triode region, okay. And that limit can be found by simply finding the quiescent drain gate voltage, add Vt to that and divide by 1 plus Gm RL. On the other side, if the input becomes if you go on increasing the amplitude on the negative half of the input cycle, what happens? The transistor is in the danger of getting cut off, all right, and that by using our analysis we said is Vgs minus Vt by 2. Okay. Now, the question is the following: what happens if you exceed that? I mean, these are the limits. So, in other words, what is the maximum amplitude you can get before the transistor gets cut off or the transistor gets into the triode region? Yeah. So, the maximum input amplitude. By the way, what happens if the transistor gets into the triode region? What comment can we make about the output waveform? So, remember, ideally the output should look like that shown in the red curve. So, if you now increase the input amplitude, right, beyond the limit for triode region operation, what happens? The waveform, I mean the waveform does this, and somewhere here the transistor enters the triode region, because it must do so now even before the input peak, correct. Once the transistor is in the triode region, ideally if the transistor was not in the triode region, we should have expected to see a waveform like that, correct. Okay. Now, what do you expect to see? Once the transistor is in the triode region, what comment can we make about the incremental gain? Two things that are happening. What happens in the triode region? The Gm decreases, and on top of it, yes, you, there is also an output resistance appearing out of nowhere. So, basically the effective incremental gain, which is Gm times the effective load resistance, is now substantially smaller than what it was when compared to when the transistor was in saturation, all right. So, what comment can you make about the waveform? If the incremental gain was GMRL, you would see a nice sine wave like that. Now, if the gain has reduced, incremental gain has reduced, what comment can you make about the waveform? Instead of seeing a trough like that, you will see a, I know what does it mean to say distorted. I am telling you that the incremental gain has reduced. So, what comment can you make? See, earlier the input voltage was like that. The input voltage was the input voltage was like that, and if you look at the output waveform, it was doing that. Okay. Now, I am telling you the gain, incremental gain is reduced. So, what comment can you make about the output voltage waveform for that portion of the input? Yes. It will become something like that. The gain is reduced, that is all that it's saying, right. Okay. If the gain, and as you can see, is this a linear phenomenon or a nonlinear phenomenon? Why? Why? Why is this a nonlinear phenomenon? No, that is there is nothing discontinuous, it is all continuous only. I mean, remember that if you have something which is linear, then regardless of the signal amplitude, regardless of what the input signal is, the incremental gain must remain the same if you are considering it to be a linear system, right. Now, what is happening once you enter triode, what is happening? The gain is dramatically reduced. It is not merely, I mean, even without triode, of course, the gain is changing, incremental gain is changing a little bit, but once you enter the triode region, the gain is reduced dramatically from that GMRL to something much smaller. Okay. So, the output instead of being like this will basically do something like that and then do. Okay. So, if you look at it as a sine wave, I mean, you can see that it is like this, taking the sine wave and chopping the bottom off. Does that make sense? Okay. Now, similarly, with the other region of operation, when the transistor gets cut off, what comment can you make about the output voltage? What happens to the output voltage? Yeah, when the transistor is cut off, in this particular example, what do we expect to see? Well, there is no current flowing through the transistor. So, the output voltage goes to VDD and remains there. So, again you can see that the top of the sine wave is getting chopped off. Okay. So, as a consequence, what comment can you make about the spectrum of the sine wave now? You put in a sine wave, if you are getting the sine wave with its either the top or the lower part chopped off. So, what is this in terms of its spectral properties? There are a lot of harmonics, so there is a lot of distortion, correct. So, what is the maximum amplitude for low distortion or distortion free operation without clipping, or I would say that is probably more accurate. It is nothing but the minimum of A max 1 and A max 2. Is that clear? Okay. So, we have discussed this principle, I mean, so we have discussed therefore the swing limits for a simple single transistor circuit. Now, nothing really changes if you have, I do not know, if you have 10,000 transistors in a big circuit, right, and you have some input and some output, and you are looking for the maximum input voltage you can put in before the output clips, okay. And let us say there are 10,000 transistors inside this inside this network, right. So, this is M1, I do not know, M9999, okay. So, how will you find out? So, this is say VO. How will we find the maximum input amplitude before the output gets distorted? Yeah. So, basically step 1 is to find the operating point. So, you will know, therefore, after you find the operating point, you will know V capital G1, V S1, V D1. Okay. Again, remember, I would like to point this out. In our example of the common source amplifier, it so turned out that the source is grounded, right, but there is no, I mean, yeah, there is it is a free country. So, you can basically, there is nothing constraining you to keep the source grounded. As we will keep progressing in this course, you will see a whole lot of circuits where the source is not grounded. Okay. And therefore, we have Vs1, Vg1, Vd1, and similarly we will have the the potentials at the drains of all the transistors you can calculate, right. And the calculation of the operating point, as we discussed earlier, is an involved process, and is most often done using a computer, because these are all a bunch of nonlinear equations, right, and have to be solved numerically. But once you find the operating point, what do we do? What is the next step? So, you draw the small signal equivalent, or the incremental circuit, and that network, how do you draw the incremental circuit? You go element by element. Every element has to be replaced by its incremental equivalent, right. So, what will you get at the end of this process? What will you get? What kind of network will you get? You will get a linear network. Once you get the incremental network, what comment can you make about the drain voltage? So once you solve the incremental network, once you solve the incremental network, what will we get? We will be able to get the incremental voltages and currents at every node and in every branch, correct. So, for example, we will be able to get the incremental voltage at each of these terminals. And what comment can you make about those incremental voltages? They will all be, at what frequency will they be? At omega, correct, because it is a linear network, all right. And what comment can we make about their amplitudes? Pardon? They will all be different amplitudes, but they will all be proportional to A, because again the incremental network is a linear network. You are exciting it with an amplitude sinusoid with amplitude A and frequency omega. So, every node voltage and every branch current will be proportional to A with some different constants of proportionality, right. So, this is say some alpha times A sin omega t, let us say this is some beta times A sin omega t, and this is some gamma times A sin omega t. And the total current, there was some quiescent current, on top of it there is an incremental current delta times A sin omega t, and so on. So, what is A max 1 is the maximum input that ensures that M1 is in saturation, right. So, what is the saturation limit that that will be, what did we, how will we figure that out? Yeah, so VD1 plus alpha A or A max 1, or rather sorry, let us assume all alpha, beta, gamma are all positive just for argument's sake, but bottom line is that you find the smallest potential of the drain, right, and the largest potential of the gate, and so we must make sure that you must solve for V d must be equal to, or V g must be equal to V d minus V t. Does it make sense? All right, the drain potential is doing something like this, the gate potential doing something else. We have to find the point at which the potential difference is the smallest, and that difference must be equal to V t. Is that clear? And similarly, V d equals V g minus V t. So, this triode limit, then cutoff limit is what? It is simply I d must be equal to delta times A, right. The delta, as you can see, is nothing but alpha, I mean gamma minus beta times G n. Okay. So, this is the cutoff limit. And therefore, what is the maximum input amplitude that will ensure that M1 is operating all the time in saturation? Yeah. So, for M1 the limit is minimum of A max 1 comma A max 2. All right. And so, now you do this for M1, M2, M3, M4 all the way up to M9999, and what is the maximum amplitude that you can use before something goes bad? Minima of all these things, right. Okay. So, it turns out that, see, once you start getting a little experience, you will basically be able to stare at the circuit, even though there are 10 transistors in the circuit, you will be able to eliminate maybe 8 or 9 of them, right, as being irrelevant as far as I mean irrelevant as far as swings are concerned, correct. It is only 2 transistors that are doing the job, right, and they are the ones where you have to actually examine the drain source voltage and the drain current. The others are all simply hanging on there, right. I mean, it is like pretty much like your lab experiments where you have 8 people in one batch. Okay. 2 fellows are the fellows who actually know what they are doing and they are doing it, the others are all hanging on there, right, just there for cosmetic value. You understand, like that. So, there is no point, there is no, all that I am intend to say is that if you see a circuit with a large number of transistors, there is no point in getting all flustered, right, and thinking it is very complicated, right. As we will keep seeing going forward, you will find that a lot of the transistors are just there for biasing or whatever, and it is not really as complicated as it seems. Okay. And finally, swing limits will only be governed by 1 or 2 transistors, and then those are the transistors that you have to look at very carefully. Does it make sense? All right. So, that was the stuff about swing. All right. So, having seen that, what do you call, the next thing that I would like to draw your attention to is the following. I mean, what we have is a working common source amplifier. There is no two ways about it.